President Harry Truman, advised by his military commanders, believed the atomic bomb was the only way to end the war quickly and decisively. It was not only a strike against Japan, it was also a message to the world and to the Soviet Union that the United States now held unmatched power. At exactly 8:15 a.m. on August 6, 1945, the B-29 bomber Enola Gay released a weapon unlike anything the world had ever seen. 43 seconds later, the bomb known as Little Boy detonated 1,100 feet above the Japanese city of Hiroshima. In that instant, a blinding white light erased 70,000 lives. By the end of that year, the toll would reach well over 140,000. Men, women, and children consumed by fire, radiation, and destruction. 3 days later, on August 9th at 11:02 a.m., a second device, nicknamed Fat Man, was dropped on Nagasaki. This time it was a plutonium bomb, more complex, more powerful. It obliterated entire neighborhoods in seconds, killing over 40,000 instantly, and leaving tens of thousands more to suffer the slow agony of radiation poisoning. These were not ordinary weapons. They were the result of one of the most secret and ambitious projects in human history, the Manhattan Project. Over 130,000 people worked in secrecy across hidden sites in Los Alamos, Oak Ridge, and Hanford, building machines capable of splitting the atom. Uranium-235 powered Little Boy, Plutonium-239 fueled Fat Man. For the first time, humanity had unlocked the energy of the universe itself, nuclear fission, releasing the destructive force of the sun inside a bomb. But why did the United States choose to use such weapons? After years of brutal fighting in the Pacific, American leaders feared that a conventional invasion of Japan would cost over 1 million Allied lives. The Japanese government showed no signs of surrender, and every battle, from Iwo Jima to Okinawa, proved how fierce their resistance would be. President Harry Truman, advised by his military commanders, believed the atomic bomb was the only way to end the war quickly and decisively. It was not only a strike against Japan, it was also a message to the world and to the Soviet Union that the United States now held unmatched power. In this documentary, we will go beyond the headlines. We will uncover the science that made the bomb possible, the secrecy that kept it hidden, and the terrible consequences of its use. Hiroshima and Nagasaki were not just cities destroyed. They were proof that human beings had entered a new era. The nuclear age had begun. In 1945, 2 bombs changed the world forever. But what made them so different, so terrifying, wasn't just their size or the cities they destroyed. It was the science behind them. The energy that leveled Hiroshima and Nagasaki came not from fire, gasoline, or TNT. It came from the heart of the atom. This is the story of nuclear fission, how it works, why it works, and how it unleashed the most destructive force ever used by man. Nuclear fission. To understand nuclear fission, we start with the smallest building block of matter, the atom. Every atom has a core, called the nucleus. That core is made up of particles, protons, which are positively charged, and neutrons, which have no charge at all. Outside that core, electrons orbit like planets around a sun. Most of the time, these atoms are stable. But certain atoms, like uranium-235 and plutonium-239, are not. They're unstable. And when their nuclei are split apart, they release energy. A lot of it. Imagine a single uranium-235 nucleus. If you hit it with a neutron, it can become unstable and split. This is fission. When it splits, it releases heat, radiation, and 2 or 3 more neutrons. Those neutrons can then go on to hit other uranium atoms, which also split and release more neutrons. This creates a chain reaction. If it's uncontrolled, the reaction happens instantly, and that's what we call an atomic explosion. But where does the energy come from? It comes from mass. Albert Einstein's famous equation, E dot or mc2, says that mass and energy are 2 forms of the same thing. When an atom splits, a tiny amount of its mass is lost. That lost mass is converted into energy. In one bomb, just a few kilograms of uranium or plutonium lose a tiny amount of mass. But that mass creates a fireball, a shockwave, and temperatures hotter than the surface of the sun. During World War II, scientists discovered two elements that could sustain a chain reaction: uranium-235 and plutonium-239. Uranium-235 occurs naturally, but it's rare. In a nuclear reactor, the chain reaction is controlled. The uranium or plutonium is arranged with rods that absorb excess neutrons, keeping the reaction slow and steady. This gives us electricity. But in a bomb, everything is designed for one purpose: maximum release of energy, all at once. The fuel is shaped into a supercritical mass, the point at which the chain reaction becomes unstoppable. In less than a millionth of a second, the reaction multiplies until it explodes. Nuclear fission was more than a discovery. It was a turning point in science, warfare, and human history. For the first time, mankind had unlocked the energy that powers the stars and turned it into a weapon. At Los Alamos, scientists knew what they were creating. Some were afraid, some were fascinated. All understood the stakes. When the first test bomb exploded in the desert of New Mexico in July 1945, it turned the night into day. One scientist, quoting the Hindu scripture, said, "Now I am become death, the destroyer of worlds." But nuclear fission alone wasn't enough. It took vision, leadership, secrecy, and massive infrastructure to turn theory into reality. In the next chapter, we go inside the Manhattan Project, the most ambitious and secret military program the world had ever seen. Stay with us. On the morning of August 6, 1945, at 8:15 a.m., the aircraft Enola Gay released the weapon later called Little Boy. It was the first nuclear weapon used in war, and the first time the energy of the atom was deliberately unleashed over a city. Little Boy's design was different from the second weapon used 3 days later. In simple terms, Little Boy relied on uranium, a rare isotope, U-235, to produce a rapid, self-sustaining chain reaction. When the chain reaction ran away, a vast amount of energy was released in an instant. An intense flash of light, a crushing shockwave, and a searing thermal pulse that set buildings and people aflame. It helps to think about what chain reaction means without getting into technical instructions. A small number of unstable atomic nuclei, once prompted, split and release energy and more neutrons. Those neutrons prompt more nuclei to split, and the process multiplies almost instantly. In a weaponized device, the fuel is assembled in a geometry and mass that allow the chain reaction to proceed without control until the material is consumed in the fission process. The result is an energy release measured in kilotons of TNT. Little Boy's explosive yield is commonly cited at roughly 15 kilotons. That yield determines the size of the fireball, the reach of the blast wave, the thermal radiation, and the zones of structural and human damage radiating outward from the detonation point. Damage from such an explosion falls into overlapping zones. Closest to ground zero is the fireball, the intensely hot sphere of vaporized material and superheated air, which for a weapon of roughly 15 kilotons extends on the order of a few thousand feet across and instantly destroys anything inside that sphere. Outside the fireball, intense overpressure causes near-total structural collapse and lethal injuries. Moving farther out, the blast still shatters buildings, overturns vehicles, and creates deadly flying debris. Thermal radiation produces severe to third-degree burns for people exposed in the open over substantial distances, and lighter thermal burns and broken glass extend even farther. On top of the immediate blast and heat, prompt ionizing radiation near the center added another lethal effect for those close enough, and fallout later exposed others downwind. Because viewers often ask how large these zones are, here are approximate conservative radii and the equivalent areas, intended only to give scale, not exact precision. For a Mont 15 kiloton surface or airburst, a rough set of illustrative radii, and their areas look like this. A fireball radius on the order of 0.2 miles, an area of about 0.126 square miles, which is roughly 3,503 square feet. A near-total destruction radius around 0.6 miles, an area of about 1.13 square miles, roughly 31,529,728 square feet. heavy structural damage and widespread collapse out to about 1.0 mile, an area of about 3.14 square miles, roughly 82,577 square feet. Thermal and severe burn exposures extending to roughly 1.5 miles, an area of about 7.07 square miles, roughly 197,067 square feet. Lighter damage, broken windows, and gust effects potentially felt out to 3.0 miles, an area of about 28.27 square miles, roughly 788,243,190 square feet. Put another way, a single square mile contains 27,878,400 square feet. The most destructive zones close to ground zero therefore measure in the millions of square feet, and the broader damage footprint stretches into the tens or hundreds of millions of square feet. Those numbers help explain how an instant of energy release can devastate entire neighborhoods, wiping out infrastructure, generating fires that coalesce into firestorms, and causing casualties both immediately and over time from radiation and collapsing systems. It is important to remember these figures are approximate and depend on many factors: the exact yield, height of burst, local topography, building density and construction, and whether the explosion occurs over land or water. Hiroshima's actual pattern of destruction and casualties was shaped by the city's urban layout, weather that day, and the fact that Little Boy detonated as an airburst, a choice that maximized blast and thermal damage over a broad area rather than concentrating it at a single point. The terrible human toll was the product of blast, heat, fire, and radiation acting together. And the physical measurements above are only one way to grasp the scale of what was unleashed. Fat Man, the plutonium bomb. On July 16, 1945, at 5:29 a.m. Mountain Wartime, the desert at the Trinity test site flashed white, and the night turned to day. The weapon that exploded that morning proved a new and far more complex path to nuclear destruction, the design later used over Nagasaki and called Fat Man. Unlike Little Boy, which used a simple gun-type assembly to bring two pieces of uranium together, Fat Man used plutonium and a precisely timed implosion to compress a subcritical core into a supercritical mass. That implosion design required shaped high explosives, arranged as 32 separate detonators, firing with near-perfect simultaneity, to squeeze the plutonium into the density needed for a runaway chain reaction. It was engineering at the bleeding edge. Fast electronics, machining tolerances measured in thousandths of an inch, and a detonator network that had to work perfectly, or the weapon would fizzle. Plutonium itself is not found ready-made in nature. It was manufactured in production reactors at sites like Hanford, where uranium fuel rods were irradiated and transmuted, then chemically separated to extract plutonium-239. This material behaved differently from uranium-235, because reactor-bred plutonium contains small amounts of other isotopes that raise the risk of premature neutron emission. That risk is why the implosion method was chosen. It forces the core to achieve supercriticality by compression, rather than by simply assembling pieces together. The implosion design also became the technical blueprint for nearly all nuclear weapons that followed, because it allowed more compact, efficient, and higher-yield devices. Technically, Fat Man worked by surrounding a roughly spherical plutonium core with a tamper, explosive lenses, and a fast-acting initiator at the center. The explosive lenses were not lenses of glass, but rings of differing explosives shaped to produce a uniform inward pressure wave. When detonated, these waves converged and compressed the core to several times its ordinary density. That compression increased the probability that neutrons released by fission would hit nearby nuclei instead of escaping. Once the core passed a critical density, the chain reaction multiplied in microseconds and released energy measured in kilotons of TNT. The bomb dropped on Nagasaki on August 9, 1945, produced an explosive yield commonly estimated at about 21 kilotons. Yield determines the size of the fireball, the reach of the blast over pressure, the radius of lethal thermal radiation, and the footprint of destruction. For a weapon of roughly 21 kilotons, conservative illustrative zones look like this in approximate square feet: a fireball radius near 0.25 miles, corresponding to an area of about 5,473,911 square feet, a near total destruction radius around 0.7 miles, about 42,915,463 square feet, a zone of heavy structural damage out to roughly 1.2 miles, about 126,118,910 square feet, severe thermal burn exposure extending to about 1.8 miles, about 283,767,548 square feet, and lighter damage, shattered windows, and gust effects potentially felt out to 3.5 miles, an area on the order of 1,072,086,564 square feet. These figures vary with exact yield, burst height, local topography, weather, and the density and construction of buildings, but they give a sense of the enormous ground area that a single airburst can affect. At Nagasaki, the terrain also changed the pattern of destruction. Unlike the relatively flat grid of Hiroshima, Nagasaki sits in a valley with hills that partially shielded some neighborhoods and channeled blast waves in others. The resulting damage was uneven, yet catastrophic in the zones directly exposed. Casualties were high from the immediate blast and thermal injuries, and large numbers later died or suffered from radiation-related illnesses. Trinity's success had shown that the implosion method worked, but its use over a city turned the test into a weapon of mass death. Understanding the engineering of Fat Man clarifies how quickly human ingenuity can be transformed into destructive power. It took reactors, chemistry, precision explosives, and timing systems, and it required secrecy at a scale few projects had ever known. The physics explains the mechanism, and the numbers measure the footprint of destruction, but the full story includes the human cost, the survivors, and the ethical debate that followed. Why there were two designs? The Manhattan Project pursued two routes because of material constraints and technical risks. Uranium-235, U-235, occurs in nature but is extremely rare, and separating it from common uranium, U-238, is slow and expensive. Plutonium-239, Pu-239, can be manufactured in reactors, but reactor-bred plutonium contains small amounts of other isotopes, notably Pu-240, that make a simple gun-type assembly unreliable because those isotopes can emit neutrons prematurely and cause a fizzle. So, gun-type, little boy, uranium. Mechanically simple, fire one subcritical piece into another to form a supercritical mass. Low technical risk for the mechanism, so it didn't require a full-scale test before use. But it needs a lot of U-235, which is hard to produce. Implosion, Fat Man, plutonium, technically complex. Carefully shaped high explosives compress a plutonium core to supercritical density. Chosen because Pu-239 from reactors needed a rapid, symmetric compression to avoid premature initiation. Implosion required a test, Trinity, to validate the design. Efficiency per fissile mass. The implosion design was more efficient. Compression raises the core density and reduces neutron leakage, so less plutonium produced a larger chain reaction than an equivalent mass of uranium in a gun design. Yield scalability. Implosion allows for more sophisticated engineering, tamping, boosting, staging, and thus higher yields and smaller weapon size for the same yield. That's why the implosion method became the basis for nearly all post-1945 nuclear weapons. Technically, yield and destructive capability. Fat Man had a higher estimated yield, by 21 kilotons, than Little Boy, by 15 kilotons. Because of the implosion method and denser core, Fat Man was more powerful, and pound for pound of fissile material, far more efficient. On that purely physical measure, Fat Man was the more destructive design. In practice, actual damage and casualties, destruction is affected by more than yield, burst altitude, urban layout, building construction, population density, and terrain matter a lot. Hiroshima was a relatively flat city with many wooden structures and an airburst height chosen to maximize blast over a wide area. That produced catastrophic firestorms and massive civilian casualties. Nagasaki's complex valley terrain and hilly layout partially shielded some areas, so despite Fat Man's higher yield, the overall pattern of destruction and immediate casualties differed. In short, Fat Man was the more powerful weapon, but Hiroshima suffered more complete large-area devastation because of target layout and the specifics of the airburst. Reliability and development. Little Boy's gun-type mechanism was simple and reliable. It was not test-fired. Fat Man's implosion required sophisticated explosives, timing, and electronics. It had to be tested, Trinity, to be trusted. Post-war legacy. Implosion's advantages, efficiency, compactness, and potential for boosting, staging, made it the template for future strategic weapons. Gun-type bombs were essentially a one-off historically because they are wasteful of U-235 and not easily scalable. The implosion plutonium design, Fat Man, was technically more efficient and capable of greater destructive power per kilogram of fissile material. The gun-type uranium design, Little Boy, was simpler and reliable without a full test, which is why it was used first. Actual destruction on the ground depended heavily on burst height, city layout, building types, and terrain, which is why Hiroshima, Little Boy, lower yield, and Nagasaki, Fat Man, higher yield, produced different patterns and scales of devastation. Aftermath, casualties and destruction, radiation sickness, long-term effects, Japan's surrender, global reaction. The bombings of Hiroshima and Nagasaki did not end when the fireballs faded. They left behind a devastation so vast that entire cities lay in ruins and hundreds of thousands of lives were torn apart. Hiroshima, struck first, saw more than 70,000 people killed instantly. What set these weapons apart from all others was not only their raw explosive force, but the invisible legacy they left behind. Survivors, later called hibakusha, faced radiation sickness in the days and weeks that followed. Symptoms began with nausea, hair loss, and bleeding. Many who seemed uninjured at first collapsed within days. Long-term effects stretched across decades, higher rates of leukemia and other cancers, chronic illnesses, and genetic damage that worried survivors about their children's futures. The bomb had not just destroyed, it had poisoned. Japan's leaders, faced with an enemy that could destroy entire cities with a single weapon, weighed their choices. On August 15, 1945, Emperor Hirohito addressed his people in a radio broadcast, an unprecedented act. He told them the war had to end, that to continue would mean not just the destruction of the nation, but the extinction of civilization itself. For many Japanese who had never heard the emperor's voice, his surrender speech marked both a national collapse and a moment of relief. The war was over, though at an unbearable cost. The global reaction was one of shock, awe, and fear. In Allied countries, some celebrated the bombs as the weapons that ended the war quickly and saved countless soldiers from an invasion of Japan. In Japan and much of the world, horror dominated as the scale of human suffering became clear. Scientists who had built the bomb wrestled with guilt. Some argued it should never have been used, while others insisted it had been the only way to force surrender. World leaders saw the dawn of a new age, a nuclear age, where one bomb could mean the death of a city, and one arsenal could end civilization. The aftermath of Hiroshima and Nagasaki was not just physical destruction. It was the birth of a fear that reshaped geopolitics, strategy, and human imagination for the rest of the 20th century. These were no longer simply weapons of war. They had become symbols of humanity's power to destroy itself.